Characterizations of invertible matrices. This section here is going to be highly theoretical and therefore awesome. Alright, so let's jump right into it. Notice I say, get out the old gilded page at the front of your notebooks, because we are about to lay the smack down with A through L here. Let's see, what's already on your page? I believe you already have G, H, E, and possibly C and D. Some combination or subset of those, rather. So add the rest of these to that, please. The proof, as I note here, that'll come out in class and partially as some homework. And just to kind of give y'all some incentive, I had a student the first time I taught this at Springs here. I showed this theorem, and the next day in class, he had come through and proved all of them were equivalent on his own. So no pressure at all. All right, anyways, I say we have a square matrix here, and all the following are equivalent. So the big one is we have A as an invertible matrix. Well, that is equivalent to A's row equivalent to identity. We have n pivots. The homogeneous equation only has trivial solutions, and so on. So the quantity of things to allow us to say a matrix is invertible is profound. You should really have all these committed to memory. And like I say, we'll prove this in class. But for now, why don't we try to apply it? Back to the previous slide and picking the one that makes you the happiest. All right, so the first question I ask you, is this matrix invertible? This is simply a matter of going. Well, when I have a 2 by 2 matrix, what I'll often do is just use the characterization of the columns form a linearly independent set. Now, why do I use that in the 2 by 2 case? Because when I only have 2 vectors, it's trivial to find out if they're linearly independent. All I need to do is ask, are they multiples of each other? Well, yeah, they are, because if I take that particular one and multiply it by 1/2, and take this particular one and multiply it by -1/3, I end up with the same vector. So that gives me a dependence relation between the columns of this particular matrix. So the punchline, not invertible. I can write this in other ways. This is not an element of GL, or I could say it's a singular matrix, however I want to write this. And that's because the columns of the matrix are linearly dependent. Okay? So that's pretty quick. All right. Is an upper triangular matrix with 0 not on the diagonal invertible? All right, so let's think about what we have here. We have some matrix. We have its diagonal. This is all 0 down here, and we have no idea what's up here. So that's an upper triangular matrix. Now, I do know that 0 does not appear in that diagonal. Now, I should actually... We can't answer this question right now. We need to assume it's square, right? So, sorry about that. Yeah, so if we have a square matrix, can we definitively say that it is going to be invertible or not? Now, going back to our inverse matrix theorem, I contend that the easiest way of seeing this is as follows. We know that in a square matrix, we want the pivots to all appear along the diagonal. Well, if 0 is never on the diagonal, then that means that the matrix has all of its pivots. And characterization, I believe it is C, which is, A has n pivots for an n by n matrix. That gives it to us. So the matrix has all of its pivots, therefore it's invertible. So the answer, is it invertible? Yes. Has all of its pivots. Okay? And, I really should be careful here, because I should say all of its n pivots, and then parenthetically say, and the matrix is n by n. I'll let you all ponder why I really should specify that to be the most precise in my answer. All right. Is a lower triangular matrix with 0 not on the diagonal invertible? All right. Again, let's add in square. All right, so we have our diagonal. 0 is above that. We have no idea what appears down here, but we do know on this diagonal 0 is not in there. All right. Now, this one is really nice because it allows me to do something. So let's say this matrix is A. If I think about A transpose, what is the structure of A transpose? Well, the transpose of a lower triangular matrix, if you think about it, is going to be an upper triangular matrix. And it fixes the diagonal, right? So I do not introduce any zeros to our diagonal. Now, if you think back to our invertible matrix theorem, the very last condition is A transpose is invertible. Well, in this case, A transpose is invertible because we actually showed that in 2 up here. Because if an upper triangular matrix doesn't have 0 on a diagonal, then it's invertible. So therefore, A must be invertible. So that's the slick way of showing that. So the answer, if I want to be really nice about this, let's ignore all the dimensionality, mentioning how it's n by n and such. I think we all know that has to be mentioned, but for the sake of brevity, what I'll say here is we note the transpose of a lower triangular matrix is upper triangular. Since the transpose of our lower triangular matrix is an invertible upper triangular matrix, I'll say C box 2 above, we have A is invertible. All right. Is a diagonal matrix with 0 not on the diagonal invertible? Well, this is really easy because it goes back into these. If you think about it, if you're diagonal, then you're automatically upper triangular or lower triangular. It's a matter of perspective. And so, yes, because I can view this triangle as this diagonal matrix as upper or lower, and therefore I get invertibility. So very straightforward. All right. Now, definition. So we're going to say a linear transformation, notice we're going from Rn to Rn here, is invertible, non-singular, however you want to phrase it, if there's another transformation on the same dimensionalities such that both compositions give me the identity. Well, this is something we already know because this is saying that, well, it's actually just saying what the theorem says right here, which is a linear transformation with corresponding matrix A is invertible if and only if the actual matrix is invertible. Okay, so it's really us exploiting this one-to-one correspondence between linear transformations on finite-dimensional vector spaces and invertible matrices. So again, not surprising whatsoever. All right. Question. Is this linear transformation invertible? Well, that's actually a really straightforward question. Because if you look at this, oh my goodness, that's a horrible line, particular definition, how do I write this as a matrix? Well, that would be -4, 6, 6, -9, xy basically, wouldn't it be? Well, on the last slide, didn't we already show that this matrix right here is not invertible because the columns were dependent? So what that means for us is if this matrix, which corresponds to this transformation, is not invertible, then that means the transformation is not invertible. So what I say about a transformation can come directly from its matrix form. So, no. Is it invertible? A big old nope. It's simply an application of this theorem. All right, let's do a couple more applications. Here's one. So suppose we have ABX equals 0 has a non-trivial solution. What does this imply about AB? This turns out to be fairly straightforward. So we know by the inverse matrix theorem that if ABX equals 0 has only the trivial solution, then, well, that's actually, it's an if and only if, AB is invertible. Well, what I'm saying here is it has a non-trivial solution. So I've negated the only, and therefore I negate the belonging of this matrix to GL. So what's that say about AB? It says that AB is singular. Not so bad. Next up, suppose AX equals B does not have a solution if B happens to be this particular vector. What does this imply about A? Again, by the inverse matrix theorem, it says that A is invertible if and only if AX equals B has a solution for every B. Well, we found a particular B where this statement right here is false. Therefore, this statement here must be false. So again, A is singular. So this is really, these two things serve as a prototype of how you apply the theorem in general.